Well, good morning, chemistry students. It's Wednesday, April 29th, 2020. We'll have a little bit of chemistry here today. So today, what I want to do is, one, just go through and practice another Lewis structure. Just check how things are going with that. Hopefully you can check yourselves. And then the second thing, the main topic today is that we're going to look at bond dissociation energy. So I can define bond dissociation energy, and I can analyze simple reactions in terms of the energy changes that happen. All right, first of all, let's look at the Lewis structure. So BrO2 with a single minus is called bromite. And I would like you to pause the video for a few seconds, well, maybe a minute, and draw out a Lewis structure for bromite. Go for it. Here's hoping that you did that and had some success, but let's talk through it. If we look at our steps, the first thing we do is we count up how many valence electrons we're working with. So bromine comes with 7, and oxygen comes with 6, but there's 2 oxygens, so we have a 7, a 6, a 6, and then it's a polyatomic ion, so it has 1 extra electron. And if we add that all together, let's see, 7 and 1 is 8, and 6 and 6 is 12, and 8 and 12 is 20. We have 20 electrons. Okay, so our second step said, how many electrons do the atoms want? Well, they each want to fill up an octet. So bromine wants an octet, oxygen wants an octet, the other oxygen wants an octet. And if you add that up, you need 24 electrons. Which means the difference between these two is they have to share 4 electrons, and that would be 2 bonds. So we just figured out there's going to be just 2 bonds. Okay? Next step, we guess on our central atom. Okay, a little bit of a weird one. Oxygen and bromine, if you look at them on the periodic table, bromine's kind of down here, but oxygen's over here. Which one's closest to this magic corner with the highest electronegativity? Well, it turns out oxygen is. Oxygen is the second most electronegative element on the planet, behind fluorine. So bromine's less electronegative. I think one of the keys here is that bromine is the singular one. Now, if you look at the valence electrons, oxygen looks like it wants to make more bonds. But 2 of the 3 things that we said we're going to look at are pointing towards bromine as the center. And I think the one that wins out in my mind here is that it's the center, or it's the singular one. So I'm going to put bromine in the middle, and I'm going to put an oxygen and an oxygen. And we got 2 bonds, so, well, we have to attach these atoms together. So far, with those 2 bonds, I've used 4 valence electrons. I have 16 more that I can use, and I got to try to fill up the octets. So I would need 2, 4, 6 over there, 8, 10, 12 over here, and then bromine needs more. Bromine right now has 4 by it. Let's see, I was up to 12, 14, 16, and then the 2 bonds makes 20 electrons. Oh, everybody's got an octet. Everybody's happy. We're not quite done. Remember, there's one last step, because this entire structure has 1 extra electron. We don't know exactly which electron that is. We just know there's 1 extra electron, so we're going to put a single minus charge. All right, hopefully you had some success with that. If not, hopefully you watched through again and saw the process one more time, because drawing these Lewis structures is a key for what we're doing moving forward. Let's talk about this bond dissociation energy, also sometimes just called bond energy. So, a bond is an attraction between atoms. And you think about, let's just think about trying to break an attraction, okay? If you got to break attraction, it's going to take energy to cause that break. What's harder to understand and visualize, but when you think about it, makes sense, is that The same amount of energy it requires to break that bond is the energy that we must get released when we form that bond. We have to put energy into breaking bonds. We get energy when we form bonds. So the bond association energy is the energy required to break bonds, but also the energy released if you form bonds. So a lot of words here, but let's think about why atoms form bonds. Okay? So we've said that a chemical bond is an attraction between atoms. And then when we looked at it more, we found out that really it comes down to attractions with the valence electrons. Okay? Atoms are attracted to their own valence electrons. Atoms are attracted to the valence electrons of other atoms. There's attractions. There's also some repulsions. Two nuclei repel each other. The electron cloud, two atoms repel each other. But then you have the attractions between nuclei and electron clouds. But at the heart of it all, here's what's happened. When two atoms bond with each other, they're in an overall lower energy state than when they're separated. It really is all about energy. Okay? If you were here in the classroom and Mr. Rupp is getting a little boring or something, not that that would ever happen, but you're really tired, you fall asleep. Where do you go when you fall asleep? Well, you slide down in your desk. Your head goes down onto your desk. Maybe you slide right out onto the floor. You're going to a lower energy state. When atoms form bonds with each other, they go to a lower energy state. If they don't go to a lower energy state, well, then they're not likely to do that. Okay? We human beings have learned to apply energy to make atoms sometimes do some things that they wouldn't otherwise do. But normally, when atoms form bonds, they go to a lower energy. So here's just a diagram. You think of a graph, and on this scale we've got energy, so increasing energy. So here I drew my two atoms separated from each other, and they have a certain energy. Boom. Okay? Here's the two atoms bonded to each other. They're at a different energy. Well, okay, so here's that change in energy from one to another. So if we form the bond, we're going to get this energy released. Okay? They were here. They're now at a lower state. Where'd that energy go? It went off into the environment somehow. If we go this way, if we break the bond, we're going to have to put that energy in to making that happen. If energy is released when a bond is formed, okay, released, that's exothermic, outward, okay? You leave a building at the exit, exo, same root there, exit, exo, outward, energy is released. If energy is required to break a bond, that's endothermic. You come into the building through the entrance, endo, en, inward. If you got to put heat in, that's endothermic. So here I've got some pictures of some handshakes. So I want you to imagine that these represent attractions between two atoms. Now, which of these is going to be easiest to break? I think you can see that, if these two people, this is their connection, their attraction, and we want to separate them, so I grab one and you grab another and we pull them apart, that's going to be a lot easier to break that attraction than it is these. And this here, that's a very strong attraction, okay? If I've got somebody in that kind of grip, it's going to take quite a lot of energy to pull me apart from the other. So there's different bonds out there. Some atoms have weak attractions for each other. Some atoms have really strong attractions for each other. But the stronger the bond, the more energy is required to break it. So not all bonds are equal. What I have here is a list of some bond energies. Okay? So we're saying when two hydrogens are sharing one pair of electrons, the bond energy is 435 kilojoules per mole. We haven't talked about the mole concept yet in our class. It's a very important concept in chemistry. But for right now, just think it's kind of like a dozen. It refers to a number. It's a really big number, okay? Because when one bond breaks, the energy for that individual bond is so small that it doesn't really impact our world by itself a whole lot. But atoms are really small, and there's a lot of them around, and so we count in these quantities that are much, much bigger. Okay? It's kind of like when you go to the bakery. You don't buy single donuts, you buy them by the dozen. You need a bigger amount. Okay? I have here an oxygen-oxygen double bond, and fair disclosure here. That's not correct. Okay? When you go and look at the references, they tell you that oxygen doesn't just make a double bond with itself. And I have not gone into the really deep explanations to try to figure out and understand why that is, because all the simple tools that we deal with in a beginning chemistry class would suggest to us that it's a double bond. But it just take it that experimental evidence shows that that's not really correct. So, what am I doing here? Why do I have something that's not correct? We're going to use this as a simplified model for an oxygen, okay? And you can take it up with your chemistry professors later on if you like. All right, and here's going to be a bond between oxygen and hydrogen. And we have those energies. And you see that this oxygen-oxygen double bond has a higher energy than the oxygen-hydrogen single bond, which has a higher energy than the hydrogen-hydrogen single bond. Okay. All right, now what are we going to do with this? Let's look at a very simple reaction. We're going to burn some hydrogen to make water. Yes, we can make water in chemistry. If you have hydrogen and you have oxygen and you mix them together, you know what you get? A mixture of hydrogen and oxygen. But if you give that mixture a little spark, kaboom, and you get water molecules coming out of it. Pretty cool. All right, the 2's in front of the formulas represent the number of molecules, because it turns out that you don't just get a 1-to-1, one hydrogen and one oxygen. It doesn't work. You need 2 hydrogen molecules for every 1 oxygen molecule, and gives you 2 water molecules. So I'm going to draw out structural formulas. So my hydrogen molecules are just H2, and that's 2 hydrogens with a single bond. Okay? And I've got 2 of them, so there we go. Altogether 4 atoms with 2 single bonds. And then here's my oxygen-oxygen fake double bond, remember, simplified model. Now, before I can make water molecules, I have to take these apart. So I have to break that bond and break that bond and break that bond. But then, if I break those bonds, I can start building atoms, and so then I bond these together. Okay? And each oxygen bonds to 2 hydrogens. So this is the before, and this is the after. Now, I'm using structural formulas here. And please note, this isn't the correct Lewis structure because I didn't show in my unshared pairs. I could have drawn in the unshared pairs on the oxygen. Oh, then I would also draw in. Okay? For what we're doing here, though, the structural formula works just fine without the full Lewis structure. All right. This arrow in a chemical equation separates what you start with from what you finish with. These are called reactants. These are called products. I'm going to use circular definitions. Reactants react. Products are produced. Okay? So we have to break these bonds before we can form these bonds. Wrong way. All right. Over here, we've got these hydrogen-hydrogen bonds, which says takes 435 kilojoules per mole to break them. But we've got 2. Now, even though this says per mole, the way this equation is written, it's proportional. Okay? For every 2 moles, well, let's see. For every 2 hydrogen molecules, I need 1 oxygen molecule. But then for 200 hydrogens, I need 100 oxygen. For 2 billion hydrogens, I need 1 billion oxygen. for 2 moles of hydrogen, I'd need 1 mole of oxygen. It's all proportional. So I've got 2 times the 435 kilojoules, and then I've got just 1 times the 498 kilojoules. And when I add that all up, to break all of these bonds would take 1,368 kilojoules per mole. And I'm saying, I got a mole of these and a mole of these and a mole of these. Okay. All right, over here, now I'm going to build these. And each of these molecules has 2 oxygen-hydrogen bonds. So we got 4 bonds altogether at the 464 kilojoules. That's 1,865 kilojoules. Now look, you can see that the energy that was required over here is less than the energy we get over here. So from this equation, there's going to be a net release of energy. More energy is given off than was put in, 488 kilojoules. So the overall reaction is exothermic. All right, let's watch that. I don't know how this is going to work. Give me a second.
So let's take a look at the reaction of hydrogen and oxygen.
I'm going to turn that up and see if you can hear it.
Keep the hydrogen in. And actually, I filled it from the bottom, so there's a opening on the bottom. And on the top here, I have an opening. If I like this baby, what happened? What do you think was going to happen? What do you think was going to happen? Well, you've seen the hydrogen-oxygen reaction before. But remember that in order for hydrogen and oxygen to react together, we have both hydrogen and oxygen. If I have a can filled with hydrogen without oxygen, you can't have a reaction. I only get a reaction when the hydrogen escapes from it.
All right, the sound was really terrible, and I don't know if you could see any of that, so I'm going to just post that little video because it's kind of cool, and I'd like you to be able to hear what he says. So anyway, I was trying to show you the reaction of hydrogen and oxygen. So I'm going to build in an exercise right into this video right now. So when we light our burners in class, we've got methane, which is CH4, and we combine it with oxygen from the air, which is O2, and it reacts to form carbon dioxide and water. Now, you've been writing Lewis structures, so I want you to try to write out Lewis structures for each of those. Then I want you to break down, look at those Lewis structures, count how many bonds you have, and add up the energy of all the bonds in the reactants. Okay, I missed a step in here, so I'm adding it in right now. Do the same thing, add up the energy for all the bonds in the products. And then I want you to talk about with me does this reaction use energy? Is it endothermic, or does it release energy, exothermic? And how much energy? Okay, so that's an exercise I want you to do with today's assignment. And I'm going to go and type that in right now while we're still on the video. So there you go, little exercise for you to try, and that's it for today's video. See you tomorrow.